This is multivariable calculus, and in this video I'm going to talk about section 14.3, which is going to be focused on partial derivatives. Now obviously this is a very important topic in this unit, since the unit is titled partial derivatives. What we're going to learn today is really how to take a partial derivative and how to understand what a partial derivative actually means. So talked about this a lot as we've been going through the last couple of sections, the idea that we're taking things that we were doing in 2 dimensions and that we're now expanding them into 3 dimensions or more. And that same theme is going to continue on today. So when we take these partial derivatives, essentially what we're doing is we're looking at functions of several variables. Typically for us, it's going to be like a function of x and y. And when we take the derivative, before, if you think about what we did in Calculus BC, we would get like dy dx, the change in y with respect to x. Well, the problem we have now is we have a function dependent on more than one variable. So I can't take the derivative with respect to 2 different variables at the same time. So what we're going to do is we're going to take what's called a partial derivative, where we look at what happens, how is our function changing with respect to a change in just one of the variables at a time. And so this is what this partial derivative definition of derivative notation is showing. So first of all, you see the notation for a partial derivative here. We've got this f with the subscript x, and that's going to tell me it's the partial derivative of this function f with respect to x. And then you can see we've got f subscript y, partial derivative with respect to y. But look at the form for the definition of a derivative. It looks a lot like what we saw when we were dealing in 2 dimensions. The only difference now is I've got that f of x plus h minus f of x divided by h, limit as h approaches 0. But what we're doing with the y is we're just saying the y is going to be held constant. So when we take the partial derivative with respect to x, the y is held constant. When we take the partial derivative with respect to y, the x is held constant. So from the standpoint of how do you actually take a partial derivative, you sort of treat whatever other variables are there as constant. So if I'm taking the partial derivative with respect to x, if there's a y and a z and any other variable, those are all constant values from the derivative rule perspective. All right, so now from the perspective of notation, we have a lot of different notations that we can use for this, and it's all dependent on sort of what's convenient for us. So the first one is the one that I just showed you. So we've got this f with the subscript x, or sometimes you just see it written like that. But another notation you're going to see is called the Dell notation. So since we're taking a derivative in a multivariable setting, we don't use the d like we did in a 2-dimensional setting. So we don't have like a dy dx, we have del f del x. And that's indicating it's a partial derivative with respect to x. If I write df dx, that means I'm taking the derivative with respect to x, and that also means that my function has to be a function of a single variable. So a big difference between the del and the d. Okay, so you can also see here del z, del x. Usually our z is going to be like our function. And then you can see f1. Well, that gets a little trickier, because if I write f1, that means I'm taking the first partial derivative with respect to a certain variable. And we'll get into that notation a little bit more later on, but that can be a little bit tricky sometimes. Same thing here. We've got this capital D. That's the first derivative of that function, in this case with respect to x, or the capital D with the subscript x is the partial derivative of that function with respect to x. Okay, so when we find these partial derivatives, we are just essentially going to hold everything else constant. That's what this rule at the bottom says. So we're going to go through a few examples here, and I'm going to show you how this works, and then I'm going to have you try some of these. So a lot of this is going to be about notation more than actually taking the derivatives, because our derivative rules haven't really changed. It's just that we're now taking these partial derivatives. Okay, so on this first example, it says find the partial derivative with respect to x and the partial derivative with respect to y for this function, and use those partial derivatives to compute the partial derivative at the point 1, 3. Okay, so let's start with the partial derivative with respect to x. Now, when I'm looking at this function, I am going to take the derivative when I do the partial derivative with respect to x, and I'm going to take it as if the y terms that are there are just constant values. So in some sense, they sort of get ignored. So for this first term, really, it's like 2y squared x cubed, right? So the only rule that I need to use is the power rule for the x cubed term. So I'm going to get 6x squared y squared. And then this 2y, well, that's like having the derivative of a constant. That just becomes 0. And then the derivative of 4x is just 4. So there's my x partial derivative. Now let's look at the y partial derivative. So when I take my y partial, now the x gets treated as a constant. So I've got 2x cubed y squared. Well, the only rule I have to use here is the power rule. So I'm going to get 4x cubed y. The derivative of 2y is just 2. And the derivative of 4x is going to be 0 because x is a constant. All right, so the other part they asked us to do here was they asked us to substitute an actual value in. So the 0.13, that means we're going to plug in 1 for x and 3 for y. And if you plug that in, you're going to get 58. And what that is telling me is the rate of change in the x direction when y is held constant at the 0.13. So it's sort of like we get two different slopes. We're looking at the slope in the x direction, and then over here, we're going to look at the slope in the y direction. If I evaluate this at the 0.13, I get 14. So my function is changing at a slope of 58 if I'm looking in the x direction. It's at a slope of 14 if I'm looking in the y direction. And remember, we're thinking of this three-dimensionally right now. So you can kind of envision what that would look like three-dimensionally. All right, on this next problem, we are asked to find del z del x and del z del y if z is equal to x to the fourth sine xy cubed. So it's really the same thing. The only difference here is we're going to be using different notation as we work through the problem. So my del z del x is going to be the derivative of this expression as if y was held constant. So I'm going to have a product rule here this time. So 4x cubed sine xy cubed. And then for the second part of this, I have x to the fourth times the derivative of this sine expression. So that would be x to the fourth times the cosine of xy cubed. And then using my chain rule, the derivative of the inside is going to be y cubed. Okay, so that would be my x partial. Now let's do the same thing with the y. Del z del y. Sometimes my del's look a little bit like 2's. I have to kind of try to keep them neat sometimes because it'll definitely start to look like a 2 instead of a del. Okay, so now when I take the y partial here, there's really only one term when I'm looking at it from the y perspective. And what I'm going to get here is x to the fourth cosine of xy cubed times the derivative of the inside, which would be 3xy squared. Okay, so notice that depending on whether I'm taking the derivative with respect to x or with respect to y, I really sort of treat this in a different way from a derivative rule perspective. Okay, but not very difficult to do. All right, let's take a look at a really simple application type of problem. It says the wind chill temperature index is given by the formula W is, and we have this function here, compute the partial derivative of W with respect to V at the point T 25, V 10, and interpret this partial derivative as a rate of change. Okay, so I want to get the partial derivative with respect to V. Okay, so I'm going to assume V here is talking about the velocity. But if I take my partial derivative with respect to V, what I'm going to end up with here, all of these terms are just going to become 0, right? So that part just sort of goes away. And then I have all of this stuff out here, which is essentially just a constant since I'm taking the derivative with respect to V. And I'm just going to do my power rule. And that's going to give me 0.16 times all of this, 0.4275 T minus 35.75. And remember, we're doing the power rule here, so that would be V to the negative 0.84 power. Okay, so that's the rate of change of my wind chill temperature as velocity changes and temperature is held constant. So I'm sort of looking at how does velocity by itself impact the wind chill temperature. Okay, so Now, when I plug in the point that they've given us here, the point 2510, we're going to plug in 25 for temperature. We're going to plug in 10 for that velocity, and we get about negative 0.58 degrees Fahrenheit per mile per hour. Okay, so that's all that's really telling me is how is my wind chill temperature being impacted by a change in the velocity. All right, so I've got another example here that I want you to try. So this is fairly straightforward, but it's just describing what we're doing in a slightly different way. This is referring to the slope of the surface in the x direction, the slope of the surface in the y direction. Same thing we did before, phrased slightly differently. So take a minute, work through that, and when you come back, I'll show you the solution. All right, so here's what you should have come up with on this. Again, same idea, taking the partial derivatives. Once you get your head wrapped around it, is actually very, very simple. So the result of part A is essentially telling me the slope of my surface in the x direction is -4. So I've got a negative slope in the x direction. I have a positive slope of 61 in the y direction. Okay, so not too difficult to do. All right, let's take a look at a few more problems here. This one says, find the slope of the sphere in the y direction at the points 2, 1/3, 2/3, and 2/3, 1/3, -2/3. So I want you to do the same thing here. You've got a diagram to work off of to make this a little bit easier to understand from a conceptual standpoint. But I want you to actually go through the process and find these partial derivatives at the given points. So pause the video. When you come back, I'll show you the solution. Okay, and here's what you should have ended up with. You can see, now remember, when we're trying to read these slopes, we're just looking at how are things changing in the y direction. So in the y direction, my z is actually decreasing in value. So we have a negative slope when I'm at that first point. And you can see here on this graph, when I'm at that first point, you can see how the z value is decreasing in the y direction. The second point, it's actually increasing in the y direction. So the positive slopes and negative slopes mean the same things as what we've always thought of them. It's just that now we have to get them in pieces. We get them in an x direction, we get them in a y direction. Eventually we'll combine them all together into something that we call a gradient, which will just give us sort of the rates of change all listed together as a vector. All right, let's take a look at the next question. And on this next one, this is just a really simple type of application to get you thinking about what these things mean. It says, suppose that d is equal to the square root of x squared plus y squared is the length of the diagonal of a rectangle whose sides have lengths x and y that are allowed to vary. Find a formula for the rate of change of d with respect to x if x varies with y held constant. So we're essentially talking about an x partial derivative. And use this formula to find the rate of change of d with respect to x at the point where x is 3 and y is 4. So this isn't really a difficult problem, but I just wanted to show you what we can do on problems like this. So we have d is equal to square root of x squared plus y squared. Now remember, we want the rate of change of d with respect to x. So I'm going to do this in a slightly different way than what you might anticipate. I could just take the derivative of this in that form. It's going to be a little bit messy. I can use the chain rule. But I could also rewrite this as d squared is equal to x squared plus y squared. Now, we're taking the derivative with respect to x. So when you go through and you take that derivative, it's just like when we did implicit differentiation in two-dimensional calculus. We can take the derivative here implicitly. So on the left side, I'm going to get 2d times del z del x. Remember, we're taking the derivative with respect to x. On the right side, I'm going to get 2x. And in the end here, my rate of change of that length of that diagonal with respect to a change in x is going to be equal to x over d. Okay, and then when x is 3, y is 4, we also can get the diagonal at that point. The diagonal then would be 5 because it's just a special right triangle. And so now my change the rate of change of that length of that diagonal with respect to a change in x at the point x is 3, y is 4, would be equal to 3/5. Okay, so pretty simple to do, but just a slightly different way of going about these problems. Every once in a while, you'll come across one where implicit differentiation might be a better route to take. All right, let's take a look at just the idea of differentiability and kind of talking about how that relates to what we did in 2 dimensions versus 3 dimensions. So we have a piecewise function here. And so you can see it's xy over x squared plus y squared, where xy is not equal to the point 0, 0. And the function is being defined as 0 when xy is at the point 0, 0. So it says show that fx, xy, and fy exist at all points xy. So if I were to take my partial derivative here, fx at the point 0, 0, what I would end up with is the limit as delta x approaches 0. And what I'm doing here is I'm using the definition of a derivative, definition of a partial derivative. So that'd be f of delta x 0 minus f of 0, 0 divided by delta x would be equal to 0. Now, why is that important that I did that? Well, what I'm doing is showing that the partial derivative at the point 0, 0 does exist. I know it exists everywhere else because I've got a function here where I can definitely take the derivative, and when I'm not having a 0, 0, then my denominator is not going to be 0, so I know my derivative is defined. But at the point 0, 0, as I approach that point, my partial derivative is 0. We need to do the same thing in the y direction. So if we go through and we take the y partial derivative, we would essentially be doing the limit as delta y approaches 0 of this f y at 0, 0. And what we would have there is kind of the same thing. It would be the limit as delta y approaches 0. I'm going to have to write this pretty small here. F of 0 delta y minus f of 0, 0. Kind of running out of space there. Let me write that a little smaller. Okay, so f of 0 delta y minus f at 0, 0 divided by delta y, and that would still be equal to 0. So since we get the partial derivative existing at the point 0, 0, we know that this function is differentiable at all points. Okay, so now once we've gone that route, and sort of what we're doing there is we're looking at the left-hand derivative and the right-hand derivative and noting that they're equal. So part B, it says, explain why f is not continuous at the point 0, 0. Well, remember, for continuity, the limit value has to be equal to the function value. Well, in this case, the limit as the point xy approaches the point 0, 0 of this function does not exist, because we would have to be looking at the limit of that, which is actually one when we were looking at limits, we looked at that exact same function. That one doesn't exist. Therefore, this function is not continuous. Now, what's different about that is when we were dealing with a two-dimensional setup, in order for a function to be differentiable, the function also has to be continuous. But when we're dealing with partial derivatives, that's not necessarily the case. And that was really the point of this question, is looking at, okay, when we take partial derivatives, is continuity required? And the answer is no. Okay, so now I've just got a couple more questions here that are in some different, or I guess with more variables is the idea here. And I want you to try getting some more partial derivatives. For the first one, we've got an x partial, a y partial, and a z partial. For the second one, we have a rho partial, a theta partial, and a phi partial. So I want you to just pause the video and take these derivatives, and then we'll check over the answers. Okay, so here's what you should have ended up with here. So you can see your x partial. We've got to treat everything else as a constant, our y partial and our z partial. The big thing here is we can have functions of as many variables as we want. So the way you take the partial derivatives doesn't change, whether there's a function of 2 variables or 3 or 5 or 10. When we take a partial derivative, we're treating every other variable as a constant. So same thing with this one that's in spherical coordinates. Same idea. Everything else gets treated as a constant except for the variable that you're taking the derivative with respect to. All right, so the next thing we're going to look at is the idea of a higher partial derivative. And one of the things that's a little tricky about this is the notation. So the notation that we use, there's a lot of different ways we can write this. The first one, we don't really write it this way very often, but you can see we have this x partial, and then we're taking the x partial derivative of the x partial derivative. So more often than not, we would write it like this, fxx. You could also, on occasion, might see it written like this. Not as often, though, because that's telling me I'm taking the partial derivative with respect to the first variable and then the first variable again. Okay, sometimes we'll see it with this Dell notation. So the derivative with respect to x of del f del x. More often than not, it would be written like this, which looks similar to the derivative notation that we saw when we did second derivatives with 2 variables. Now, where this gets a little tricky is when we have what we call mixed partials. That's what we have right here. We're taking the x partial, and then once we have the x partial, we're taking the derivative of that x partial with respect to y. So this mixed partial, you can see fxy, or, and again, I don't like to use this notation as much, the derivative with respect to the first variable and then the second variable. More often than not, though, we'll use this Dell notation and this one. But notice with the Dell notation, you have to be really careful with it because of the order of things. So I'm doing del f del x, and then I'm taking the derivative with respect to y. So when you read this notation, it always shows up backwards from what you think it's going to be. You always have to read this denominator from right to left. I do the x partial and then the y partial. So that's always a little bit tricky for people at first. We have the same idea here with a mixed partial. This time we're doing y and then x. Notice that it says 2, 1. But again, if I see it this way and I read it right to left, I can see it's a y partial and then an x partial. And then we've also got this second derivative with respect to y. So all of those are going to be things that we're going to use. They work in a similar way to what we did with concavity. We're still looking at concavity, but only in certain directions. And when we start looking at the concavity with these mixed partials, it gets a little bit tricky. So we're going to get into that stuff when we talk about maximum and minimum values in a few days. Okay, so let's go through just a couple of quick examples of this. It says find the second order partial derivatives of this function. Okay, so when we have to find second partials, we always need to find our first partials first. So fx here would just be 2xy cubed plus 4x cubed y. Fy here would be equal to 3x squared y squared plus x to the 4th. Okay, so those are our first partials. Now, if I want to get my second partials, if I want all of them, there's going to be 4 of them. So the first one I'm going to write is the xx partial, meaning I'm taking the derivative again with respect to x. We would get 2y cubed plus 12x squared y. And if I get my mixed partial, I'm going to end up with, now I'm taking the derivative of fx with respect to y. I'm going to get 6xy squared plus 4y cubed, or 4x cubed. All right, so now let's do the same thing with the y partial. Okay, second derivative with respect to y here would be 6x squared, or yeah, 6x squared y, and that's it. because the second term is going to become a 0. And if I do my mixed partial, y and then x, I'm going to get 6xy squared plus 4x cubed. Okay, so not really that difficult to do. You just have to be careful that you keep everything straight in your mind. What am I taking the derivative with respect to? Okay, so notice at the end here, I got these two mixed partials. Notice that there's 6xy squared plus 4x cubed, and they're exactly the same. So the reason for that is that anytime you have mixed partial derivatives and they're both continuous on the domain that we're looking at, that means those two mixed partials are going to be the same. So a lot of times when we know what we're looking at, we'll be able to tell whether or not we're going to have mixed partials that are the same. Anytime we deal with these polynomial functions that are continuous everywhere, we know for sure our mixed partials are going to be the same. And we'll look at a few of those moving forward, and you'll kind of see how that works out. Okay, so I've got another problem here where I want you to find a higher order partial derivative. So this is actually a third partial. So we've taken the partial derivative with respect to x and then y again. So just pause the video, try that one. When you come back, I'll show you the solution. Okay, so here's what you should have ended up with. You can see on the first derivative, we took the derivative with respect to x. Next derivative was with respect to y, and then with respect to y again. So we end up with 2e to the x. So this notation that we have here, we can keep going with this as far as we want. We typically won't go past the second partial. That for our applications, we don't really have a lot of meaning beyond that. But there are situations where you can get into higher order mixed partials. All right, so we talked a little bit about the equality of the mixed partials, but here's just where it's stated out. So this is called Claro's theorem, and it says, suppose that f is defined on a disk D. So when they say on a disk D, that's just talking about the domain in the x direction and the y direction. And that disk contains the point AB. If the mixed partials are both continuous on that disk, then the mixed partials are going to be the same at any point on that disk. Okay, so this next question, it says, confirm that the mixed second order partial derivatives of the function are the same if we have f of x is the square root of x squared plus y squared. So what I want you to do is get the two mixed partials. And remember, when I say mixed partials, I'm saying fxy and fyx. I want you to get both of those, and if you've done this correctly, those should be the same. So pause the video, work that out. When you come back, I'll show you my solution. Okay, so here's what you should have ended up with those mixed partials. I didn't show all of the steps, but in the end, you get negative xy over x squared plus y squared to the 3/2 power. So sometimes with these mixed partials, I mean, when we have these rational exponents, just like when we were dealing with rational exponents in 2 dimensions, things can get a little bit messy. The algebra can get a little messy, but typically it'll work out fairly nicely in terms of simplifying things down when we have these textbook style questions. All right, last thing that I want to talk about here in this section is the idea of a partial differential equation. When you see these, the only thing we're going to do with these right now is we're going to verify solutions. At the very end of the year, if we have time, we're actually going to start solving these types of differential equations. It can be a little bit tricky. But for now, all we're going to do when we see these partial differential equations is we're going to verify solutions to partial differential equations. So what they have here, and I just wanted to show you this because you're going to see questions like this in your assignment. You're going to see questions like this on the quiz. It's just a different way of phrasing a partial derivative question. It says, show that this function is a solution to the partial differential equation del squared u over del t squared is equal to c squared del squared u over del x squared. So if you go through and take those partial derivatives and multiply the right side by c squared, what you're going to find is that you get negative c squared sine of x minus ct. You would get that on both sides. And like I said, the main reason that I want to make sure we talk about this is just so you understand why are you seeing these and what's the purpose of this right now. You're not being asked to solve the differential equation. What you're being asked to do is verify the solution to the differential equation, which just means that if this is the solution, it has to make that equation true. So keep that in mind. Okay, so that's all we have for now on partial derivatives, but keep in mind, we want to get to the point with partial derivatives where this is just second nature, like taking derivatives was in 2 dimensions. So we want to have this x partial, y partial, z partial stuff. We want to have it to where we don't have to really stop and think about it and grind through every question. We want to get to where we can take these derivatives fairly quickly.